This is our session. We are Ignition IO, and this is our session where we will introduce who we are, what we are doing, and how we are building a platform where our goal is to democratize the open source silicon design. So it's actually great to have you all here. I see so many participants here. And I see Salia sir, you have also joined, so it's great to have you here. So yeah, with that we can start now. Yes, and move to the next screen, please. Okay, so here is our agenda for today. So I'll be going over a brief introduction about who we are, then followed by the overview of what this presentation is about. Then we will briefly talk about the pain points that we usually face as a VLSI engineer working in this domain, and I'll also share how we personally face these things while working previously. Then I'll start with showing our solutions, how we are approaching this issue, how we are targeting the problems one by one. And then we will show how we have come up with our platform, which is our first step in democratizing chip design. Then after that, I'll go over to the architecture exploration demo, which we have prepared by using our own platform here. And yeah, finally we can have some interaction where you can ask your questions or give your valuable feedbacks. Please note your questions in the meanwhile. I'll ask you if you have something to ask. Please ask me at that time. Yeah. So this is our team for today's session. I am Somijit Mandal, and with me is Hassan. So we are just two engineers. We have worked in the VLSI field for some time, and now we are part of Ignition IO together with our founder, Mr. Rishabh Anand, who is currently for today's session. He is not able to join us because he had some urgent travels. But yeah, this is basically our team right now. So yeah, let's talk about what we are all about first of all and why we are here. Yeah, so let me start by thinking about software first. Yeah, so how many of you have ever thought of creating a website or a basic software or a tool? Um, Maybe you can raise your hand, or I'll just assume that at least all of us have at some point thought of creating a website or some software or tool. And currently, that is very easy given the software stack and how the world develops software. You don't need any specific technology, or let's say you are not bound by any big company for you to develop a software or website. And you can, let's say you want to develop your website, you can just go ahead and download some JavaScript libraries or some other toolboxes which are basically free to use, install and use. And the setup is also not that much of a pain, and you can just quickly get started, and as well as quickly iterate and build great software and great websites using nothing but your knowledge and your laptop or system which you are building it on. So if I have to compare this situation similarly to chip design, I think we can all agree that we can't even really think of where to start. Yeah. So if I ask any one of you to just say how many times have you thought of developing your own custom silicon, or how many times have you thought of creating, let's say, a CPU core? So that is something we tend to think of it as a far off dream, or we don't even know where to start. Yeah. But technologically, I should say that it's not something that's very critical or very much like rocket science, or you need something very special or very higher education to do that. It is something that is in the range and capability of a college student. But unfortunately, in the current scenario, how we see the chip design industry is lacking that. So it's not open. So if I have to put it simply, it's not very open, it's not very welcoming. People don't have much access to the tool chains. There aren't many tool chains that you can freely develop. If there are any tools, then those tools are behind huge paywalls, and you either have to be working in a big semiconductor industry, in a semiconductor company, or you should have access to some labs or some specific special setup to be able to even start your chip design work. So this is our goal here, this is our ideology. We want to make silicon design and chip design as much sovereign and as much accessible as possible. Having worked in the industry, we realize that it is possible to achieve that, and it's just that software has, let's say, accelerated. In the past few decades, software has accelerated quite a lot. It has become more open, it has become more secure. Many people can participate, and you don't have to be working for a, let's say, large organization to be able to write your own website or your own software. Yeah, you can be a developer, or you can be a student, you can be anyone, you can be a hobbyist, and you can start writing your websites. So for us, our goal, our dream is to make silicon approach that as much as possible. We want to see more and more engineers, more and more people, hobbyists, students, university goers, and so on. We want to see everyone being able to develop and write their design their own chips. Yeah. So this is our goal, and this is what we mean by democratizing. So democratizing means everyone has at least some access to uh, chip development. Yeah. So this is what we are all about. So let's take a quick look at the semiconductor value chain. On the top, you will see three boxes, and on the bottom, you'll see one large box. So I'll start with the top. So there are some companies who are called fabless chip designers, and you can see big names on there. There's NVIDIA, AMD, Broadcom, Qualcomm, and so on. So these companies, they develop their own design, but they don't have a fabrication facility. So of course, chip design is not like software where you write the code and just compile it and the result is in front of you. There are two aspects of chip design. That is, one is of course chip manufacturing, I should say. So one is design and one is manufacturing. So these companies, they don't have their own fabrication, but they operate in terms of design. So they design various kinds of chips. Then the arrow showing the connection between these companies goes to the foundries. So these are companies that specifically handle the fabrication aspect of these chips. So you write your design and then you send to these companies called foundries, and they are there to fabricate it for you. So basically, they realize your design into the actual silicon and send it back to you. Yeah. And then there's also testing and packaging companies. Then on the very bottom, we have the IDMs, integrated device manufacturers. So these are the companies which you can say is a combination of both the two on the top. So basically, they have their own fabs and they do their own design as well. So they don't have to go to a pure play foundry to get their chips fabricated. They can just write their own design and they have their own fabs, and they can do both the things under their own name. Yeah. And in the middle, you will see a box called Design Software R&D Tools and IP. So this is what the box for EDA is. So EDA stands for Electronic Design Automation. And as the name suggests, it's all about the automation of the chip design. So here you will see the companies like Synopsys, ARM, Cadence, Siemens, and so on. So these are the companies who help the others in this picture to develop their chips. Yeah. So they create tools, methodologies, flows, and so on, and they sell it to these companies, and then these companies use it to basically automate and largely enhance their chip design process. Yeah. So currently we fall somewhere in that red circle that you see there. So we are here to start democratizing the chip design by starting with the tools. So currently there are several tools in the open source realm as well, where you can use those tools to carry out the stages in the chip design. But these are fragmented and these are scattered. So about this, we'll see more on the next slide. But yeah, we start here, and our goal is to create a platform which will unify these various tools that are spread across. Since most of these tools are open source, so these are mostly developed by engineers, but there isn't a very large company that is backing them. And due to this reason and several other reasons, these are scattered, and basically no one is there to take care of these tools. Whereas if I have to be clear, the tools themselves are very good, and they are on par with what you get from the companies such as Synopsys, ARM, Cadence as well. So that is where we have started. Yeah, Hassan, please move to the next slide. Yeah. So, yeah, let's see how the demand and the rest of the infrastructure falls here. So we currently we see we have the AI hardware demand, yeah, and at the same time, as I said, we want something of a sovereign thing for the semiconductor as well. Currently, these are the all the solutions for EDA that exists are somehow behind the cost barrier, or you can say not openly accessible to many developers. Yeah. And recently we are seeing the open PDK emergence as well. Yeah. So on 1 June 2022, Google signed a deal with a contract with a company called I think it's Global Foundries or Skywater. Yeah, Skywater, in fact. So they created a ecosystem where now you can write your own design and go to this Skywater PDK, and they will be able to fabricate your chip. So you don't have to depend on any large foundry there. So basically, they have open sourced the PDK itself. Yeah. So as we can see, the various things exist, and from all directions, the open source is approaching. And this is a natural, you can say, natural pattern that is observed. Open source always wins. So this is what happened in the case of, let's say, software as well, few decades ago, with operating systems as well, with databases, and now. Some of you might already be working on open source AI solutions as well. So this is a pattern. Open source always catches up with the closed source, and somehow silicon or chip design is where this was lacking. And as we identified with these four columns that you see here, that the environment and the ecosystem is brewing right now. And this is the right time that there is something that unifies this. There is a platform, or you can say one roof, where we would have open IPs, open PDK, open tools, and a complete open ecosystem, which is not behind any cost barriers and well maintained. So anyone can access these things, and anyone can, let's say, create their own chips. Yeah. So this is the idea here. So all of this points to a central infrastructure demand, or something that connects all of this separate components together. Yeah, Hassan, please continue. Yeah. So this is what I already said. Software is very much open. This is the example that I started with. Anyone can go ahead and create your website or software, but silicon is currently fragmented, tool heavy, and very hard to enter. So you can't even think of, let's say, where to start with designing a chip. Yeah, and naturally, because of these reasons, iteration remains slow and constrained. Yeah, continue. Yeah. I think I will continue with this slide as well. This again reinstates the same thing, but yeah, let's go through it quickly. So currently in the software, we have AI native developer era. So this is where software has reached, where there are the automation has reached to up to such a good mark that now you don't even have to write your own code. Basically, writing code has become cheaper. Now you can automate the writing of code as well, and not just let's say workflows. Then we have previously we had the ID era as well, where we saw that great IDs, which is integrated development environments. So these were coming up, such as VS Code, and there are many. So that is what you get, so many options in the terms of development environments and not just libraries. Yeah. And even before that, we had the early tooling era where many people, many open source developers wrote great command line tools and environments. So this is where it started, and you can see because software got an early start where it has reached now. Yeah. So, but on the hardware end, as I've already said many times now, it is quite fragmented, and it's quite hard to enter the whole scene of developing our own silicon. Yeah, so this is again painting the same picture. Yeah, yeah. So these numbers that you see were a part of our own internal research. When we were doing the market study, initially we conducted some, let's say, questionnaires, and people took, not many people, but whoever took the questionnaire, they were very generous enough to share their experience with us. And we found that if not all, many of them agreed to the problem that we identified, and it's something that many people face in their day-to-day thing here. So yeah, please continue. Yeah, again, software is easily accessible. You can download it for free. There is no institutional barrier, and this is what true democratization means, where anyone from any corner of the world can download any software and just get started with it. Yeah. So yeah, we want to create a platform which is more open. It is very programmer friendly, programmers as in VLSI engineers, and it is more developer driven. So our goal is to take the components that succeeded from the software world into the chip design world. So we are not reinventing the wheel here. We are just completing what was already done in software, and software has shown us that it is quite possible, and we want to transfer the same things. As it says, shifting from manual, non-standardized flows to programmatic automation and managed reproducible environment. So software has already shown us that this works, and this is the same kind of pattern that we want to take to the hardware world. Yeah, please continue. So that was our intro on who we are and what problem we are tackling and how we have, let's say, started to tackle it. And yeah, now before going into the, let's say, our tool demo, I would like to take any questions if any of you have any. Okay, so yeah, let's get into the demo straight up. And I think I will share my screen now, Hassan, and show the demo here. Uh, Let me quickly share. Please let me know if my screen is visible.
Yeah, it is visible.
All right, yeah, great. So here you are seeing a basic GUI. So I would like to be explicit here. Right now, our tool is only CLI, and I'll quickly do igni init. So this is the name of our CLI tool, and we will be eventually building let's say, GUI layer and AI layer and many other layers on top of it. But the core of this tool is this CLI, which you will be seeing in action right now. And this is on top of cursor that I am showing you, just to show you that how easily it is integrable to already existing workflows and already existing tools that you guys are familiar with. Yeah. So actually, even before doing this, let me pull up something from the knowledge base as well. So this is how the AI agent is going to automatically suggest me how to get started with a clean workspace here. Yeah. So I'll just tell him, please give me the initial instructions to get started with the CLI. So that's all I'm gonna write. And I have previously given it the context. So it is going to go through the context and just see what it can suggest me. And yeah, let's wait for its output. So this is nothing special, honestly. We have given it our user guide. So we have a very well-defined user guide for our CLI. And this is what we have given the agent as well. And just like any developer would go through the user guide and understand what it is about, what the tool is about. Similarly, the agent is going through the user guide, and it has given me, as you can see here, it has given me a set of commands that I can simply follow, and here it even says step by step. So that's how we would approach our new project here as well. So before anything, I will simply start with the very first command here. So this is the very first command that we have. So I had already written it, and as you can see, it has entered a new shell, which is our own Igni shell. Yeah. From here on, I can write the next command and see what is available here. So I can see a few commands here. Let's say I show you the list. So here you will see a list of tools here. This is not an exhaustive list. This is just the tools that we have currently added. But yeah, here you will find a plethora of, let's say, open source tools. And going forward, we will also add the commercial tools here. Or in fact, you can even create your own tools and add to this list. It's very simple. Yeah. So, but yeah, as I said, this is currently the few tools that we have supported. We will be in the future, we will be building more and more tools and more versions of these tools. So it doesn't have to be just one version. You can have many multiple versions of the same tool as part of your development workflow. Yeah, so this is the list of tools that you can see here. And let me start some tool and show you how simple it is. Yeah. So let me clear this, and I'll follow what it is giving me. Yeah. So let's say Igni env create. So Igni env is for creating an environment, and this environment is an isolated space where you can install your tools, flows, irrespective of worrying about how you can manage them. Yeah. So the environment, one environment is separate from the other. That's why you can use, let's say, one version of tool in one environment and other one in the other. Yeah. And the management is pretty, let's say, easy here. You just write igni env help, and again you see the environment specific help options here. You can create, list, activate, deactivate, and so on. Yeah. So I'll simply igni env create a new env. Let's say, yeah. Any other questions? Yeah. Also, going forward in the next slides, you will see something on the reproducibility as well. So Like suppose you and me are a pair of professor and student, and let's say you created something, or you were able to achieve a simulation, or you were able to do a synthesis run for you which works successfully, and now you want to present it to me, me being the professor here, yeah. So in the conventional tools, or let's say in the simple flow where you can just sudo apt get install, it doesn't work. So you will end up spending most of your evening just being able to set the tools. Yeah, it doesn't work so easily. You will have to take care of the environment, the shared libs, and conflicting, let's say, dependencies and so on. So you'll have to have your professor as well. Do the whole setup thing, yeah. But in the next slides, you will see how using this platform, you can simply just with one command, you can share the exact replica of your environment with anyone. So with your professor or with your teammate or anything, which completely removes the friction of, creating reproducible environment. So that is something completely missing from standard GitHub flow, or, getting a tool like label lane or something and then working with it. So there is no way of syncing with others there. So that is something that comes natively with our tool because of the environments concept that I just showed you. Yeah. So I think Hassan, we can continue. Yeah. Okay, so this is again visual to showcase how we are like utilizing the software world's concepts for chip design as well. Yeah, we can go to the next slide. So yeah, CLI demo is already done. Please proceed. So this question has just been asked. So I think we are lagging behind in showing the PPTs. But yeah, this is what I was just saying, the design lifecycle continuity, where you can share the environments and continue the cycle. So one part of your team can take one stage of the development, and the other can take the other one without any friction in between. Yeah. So continue. Yeah. So now in the next part of this presentation, I will show you how we are utilizing our own tool in our internal projects. So this is where the first thing falls, where we are working on a virtual prototype project that comes even before RTL. Yeah. So as you can see, the orange box is idea here, and RTL is the next box, and the final box is GDS. Of course, it is highly, let's say, reduces the picture just to three boxes. But yeah, this is the you get the idea here. So today's focus is on the even the pre-RTL flow. So even before RTL, what you can do. So if you have, let's say, a customer or someone coming to you and they say that, yeah, we want to develop this kind of chip, or we want to, let's say, come up with a silicon that solves this problem. So how do you start the development process? Yeah. So this is a very crucial stage, and mostly we skip this stage and we jump directly into the RTL. Yeah. So I will show you how we are tackling this stage specifically, and how we are using our own tool for this. Yeah. So please continue. Yeah, again, this shows the various stages. So actually, the diagram that you saw before, you can say when you zoom in into that, you will see this kind of stages in the chip development pipeline. And the microarchitecture RTL decision is the stage that I'm going to show you the demo on. So how you come up with a microarchitecture, and how do you go from the concept stage on the top, and between the synthesis and functional verification is the RTL stage. So how do we tackle that? Yeah, continue. Yeah, continue, continue. All right. So this is the virtual prototype demo, and I will again share my screen and show you what we are doing there. Yeah. Just give me a moment. It's taking some time to come up. I'll share
Your
my
mute,
screen.
Somjit.
Oh yeah, sorry. I don't know when I went mute, but yeah, I'll just share my screen again. Just give me a second. Yeah, please let me know when you see my screen.
Yeah, it's his way.
Okay, yeah. So now jumping over to the virtual prototyping aspect, which is exactly what you need before writing your RTL. And in the interest of time, I'll go a little bit quicker through this so that we can complete it in time. So yeah, let's get started. I will go through what virtual prototyping itself is, what are its market applications, and how we are utilizing it in Ignition. Yeah. So, what is a virtual prototype? As the name suggests, it is something virtual and it is used for prototyping. So, this is not something that the chip design industry explicitly or alone uses. This is a very common methodology for any kind of product building. You are always going to create a virtual prototype of it, a virtual smaller version of it, and you are going to see how it works. Yeah. So a virtual prototype is a software model of a hardware system which is accurate enough for real firmware and software to run against it without any physical chip being manufactured. Yeah. It recreates the behavior of processors, memory maps, buses, and peripheral IPs in software. From the software's point of view, it is indistinguishable from the real hardware. So the idea is whenever you are going to create a chip, there is a huge time period when you start from the idea and when the day you have the actual chip in your hand. So when it is taped out, it's not like software where you can compile it and see the change. It takes its due course of time. Yeah. So the idea of virtual prototyping in chip design is to compress or shrink that huge gap between idea and your chip. Yeah. So the idea is to create a software model or let's say a simulation of the actual hardware chip. And the challenge is that it has to be accurate enough for real firmware to run on it. So when I am developing my own firmware, it should be indistinguishable whether I'm running it on the actual silicon chip or whether I'm running it on the virtual prototype. Yeah. So yeah, you can simulate the CPU. You can simulate the various peripherals in the chip. Basically, you can simulate everything in the chip that is present. Yeah. So again, talking about the hardware problem. So this is the cost of a sock respin. So respin means whenever you, let's say, whenever you have a issue in the bug. So let's take the example of when you have a issue in the software. So it is very easy to fix because you just need to pinpoint what exactly the root cause of the bug is, and then you have to change a few lines of code or write few lines more, and then it is pretty much fixed. And it takes your time, but not anything more than that. But in the case of chip design, it is a huge issue if you find a bug later in any stage of the chip design pipeline, and it shoots you back. Yeah, so you end up spending so many dollars on just reaching that stage of the development. You spend so much time, as you can see here, and at the end you will end up with a respin. So respin means basically you'll have to start the process again of the chip design right from the start, or from the point where you find the root cause of the bug, and that takes a lot of money. Yeah. And there are huge hardware software integration issues. So that means you can have bugs coming from software that runs on your silicon, and you can have individual bugs on the hardware itself, and you can also have bugs in the interface between them, so the software running on top of your hardware. So the traditional flow is looks like this, where you design your hardware, then you wait many months, and then your embedded software developers are just like sitting ducks who don't have anything to run their firmware on. Yeah. and then after so many months they discover more bugs, and then it goes for respin. So it is very bad, and this is what happens in the industry, especially in the case of complex stocks. Yeah. So virtual prototyping exists to break this cycle, or minimize it as much as possible. Yeah. So the later you find your bugs, the worse it gets. So conversely, the earlier you find it, the better it is. So the in the concept or in the VP phase itself, if you happen to find so many bugs in your design or your assumptions, then since VP is ultimately a software, you get the benefits of software there. Yeah. So it takes nothing to fix that bug, or at least it takes nothing to identify that bug. Whereas if you happen to find it later on, then it's a huge cost. Yeah. So because of the reason that VP is essentially a software, you get the benefits of software. So it is cheaper. You can develop in parallel. So meanwhile, your RTL team is working on the RTL. Your embedded guys are now no longer sitting. So they have the VP as you remember in this slide, I said that it has to be indistinguishable as possible from the real hardware. So that means the software, the embedded guys can just start writing their firmware, and they don't have to worry that when the actual silicon comes, then we will have to write it again. Because they are already working on something that is exactly like the hardware, they can freely develop it. Yeah. Again, you get rich test coverage since it is now a software. You can write regression tests, you can inject faults, you can do whatever you want, just like you develop your software. Then the biggest advantage is no hardware required. So months before your tape out is actually even possible, any engineer, whether in the RTL team or even the software team, they know that okay, the thing is already running. So I already have the behavior of the chip that is going to be taped out. Yeah. So there is no hardware requirement. So what you can really do with the VP is shown in this slide. So you can write instruction set simulators for your course. So you can simulate the entire instruction set of, let's say, a RISC-V processor or an ARM processor or even an x86 processor. So you can write it. Then you can write a virtual platform or full system model of your entire SOC. So not just your core to run the software, but you can even write, let's say, analog or mixed signal simulation. So you can simulate every part and every IP of your chip. Yeah. Then you can also write very related RTL. So suppose you have your previous generation of chip, and it already has a RTL, which means it is an already taped out chip and it is doing good in the market. Now you are developing a next version of the same product, and in that you want to include a new IP. Yeah. So in that case, you can just take the very related model of the previous RTL, and you can write your extra IP, that is the new one. You can write a simulation for that, just that, and then co-simulate both of these things together. So in this case, you didn't have to write the simulation for the whole SOC, but rather just one IP. So this is also possible. Then FPGA emulation is something even closer to the silicon or taped out or real hardware. And even with FPGA, you can run the VP in parallel. Yeah. And this is, of course, the ground truth, how the actual hardware looks like. Yeah. So the demo that I'm going to show you is around these layers. Yeah. So the full system model. So let's see how VP is used across the industry. You can quickly take a look at these cards that show that it's used in automotive, data center, pretty much everywhere. So this problem is not something specific to a single industry. Instead, it is let's say something that is faced by everyone in the industry. It doesn't matter if you are falling in any one of these. Yeah, you are going to face this fundamental issue, and that's why VP is used. VP can be used anywhere in any industry, as long as you are developing a chip and you want to shift left or let's say gain advantage by writing a software simulation. So yeah, this This diagram shows what I have already told you verbally, but yeah, let's go through it again quickly. So usually the traditional starts at RTL design. Once you are done with your verification, you go to your synthesis. And once you're again done with the synthesis, you have a red big block here, which is basically waiting for the silicon. You give your design to the foundry, then it's up, the ball is in their park and it's up to them whenever your chip gets fabricated. Meanwhile, the software developers, the firmware guys, the driver teams, and all of the teams, those who have to write some software on top of that chip, they are basically sitting here. And then they again add their own bugs, and you go for a respin. Yeah. But with VP starts even before the RTL. So you can see here it is written RTL plus VP. So whenever the specs has been frozen for your product, it goes to the VP team as well as to the RTL team. Yeah. So the RTL devs start writing their RTL code, the actual HDL code that is going to be synthesized. Meanwhile, the VP developers start in parallel, and actually the VP developers often start much before the RTL guys as well. And meanwhile, the VP reaches a good stage, good maturity. You get two advantages. Firstly, the RTL people get a very good reference of what the actual chip is going to look like, how it is actually going to behave like. Yeah, and the software people are now not blocked since the VP runs exactly like the hardware. It is going to be unblocking the software team, so now they can freely start their development. Yeah, and the biggest advantage here is you are not just getting started early, you are also discovering the bugs early. You are already predicting and analyzing the behavior of your chip, how it is going to function, how it is going to perform, how it is going to behave in certain conditions. You can add your edge cases, and you can do so many things with VP, and you can do it so early. Yeah, so that's why you see that the post boxes, the boxes that come later, are mostly green here, because all of your, or let's say most of your bugs, a large number of your bugs have already been eliminated even before the silicon has made its entry here. Yeah, so once this tape out is done, yeah, the silicon goes back to the software team, and they can already see that the software they have written for working on the VP directly runs on the chip, and everyone is happy here. Yeah. So I think I'll just skip this slide because I've already spoken a lot on this, what you can do with, let's say, VP. So yeah, actually I'll go through this one box here, which is about profile and benchmarking. So this is specifically the performance engineering aspect of virtual prototype. So consider a case where you have to create a chip product, where you have to create a silicon product, where you have no clue or no idea on the kind of workload it is going to handle. Yeah, so you don't know what kind of CPU you should use. You don't know what does the memory latency, bandwidth, and things like that look like. What kind of bus architecture should you follow? What kind of algorithm should you keep in software? And what kind of what do you need in the silicon for that? So basically, hardware software partitioning. So all such kind of questions, and even more questions, even more trends, and let's say statistics and analysis, you can easily come up with by writing a performance model of your chip. And then you can create a, let's say, a design space exploration of all the possible combination of IPs and cores that you can take. And then you are in the advantage, because after doing this step, you know exactly which core, which IP, which configurations you need to choose, so that your product is neither over engineered nor it is under engineered. So it fits perfectly, it does its job, and you are also saving on the cost. Yeah, so this is the performance engineering aspect of VP. So you can even use it for benchmarking. Yeah, rest of these I have already covered. So now finally, I will show you guys what we have done with VP at Ignition, and how we are actively using it to, let's say, drive architectural exploration work with RISC-V cores. So this is our attempt, this is part of our attempt to use our own tools and methodologies and come up with, let's say, solutions, and come up with a real SOC based on a RISC-V core and show that how VP can be useful here. Yeah. So I will quickly, let's say, get my. So I'm opening my VS Code here. So as you can see here, this is VEX RISC-V accelerator project, and you will see there are many other projects here, but this is the one that I want to show you right now. VEX RISC-V is a RISC-V, tiny RISC-V core, and this the directory that you see here is an entirely a VP of it. So you will see no RTL here and nothing that will actually synthesize, but I'm going to show you how I can still use the same architecture, same RISC-V core as the real product, and I will show you how you can actually run the software here. Okay, so I'll go to that directory, and here I have created a simple script. Let me just launch that. Yeah, so I hope you can see a terminal come up. So let me show you the most interesting thing of this terminal. Yeah. So if I open another terminal here, which is my systems, and if I do, let's say, uname -a, you will see that I am running this version of the Linux, and this is the architecture that it is showing here. Yeah, x86, because I am using an Intel i7 processor. You see that it is an Intel x86 64 processor. Yeah, architecture, and this is the version of the Linux kernel I am using, and this shell is my own system's shell. Yeah, whereas this terminal that you see looks very similar, exactly similar to just another terminal of the system. But here you see that firstly you will notice that when I let's say when I launch this script, you see something I think some of you will be familiar with. So this is the boot sequence messages that you see here, and you can see that this terminal is actually booting a Linux instance. Yeah, so I have booted a Linux instance, and you can see that I have received a TTY login. Yeah, so if I just write root here and login, you will see that I'm getting a terminal here. Yeah. So if I run uname -a here, you will see that this is different from the one that I was using in my own PC. Yeah, so this is different. And in fact, the architecture itself is different. Here it is RISC-V 32. Yeah, so this means that this terminal is coming entirely from the simulation of the chip, and I am able to access the running chip using this terminal. Yeah. Now to show that, I'll show you, I have already added some binaries in this file system that you can see here. So I'll just maybe run the most interesting one. So actually, let me run a simpler one first. So I'll just run the ignition banner. And if you notice closely, you will see a bit of a lag in this terminal here. If I type it, you will see it. This is because this is simulating the entire behavior of the LiteX RISC-V SOC, and it is also running a Linux instance on top of it. And finally, it is now going to run a executable on top of it. So naturally, there is going to be some lag in this because it is simulating so many things in this system. Yeah, and you can see my RAM usage is up as well. Hopefully, you can see this interface here. It says 77%. So this is all running on my system RAM. But you can see that I'm able to. This print is a bit, let's say, not right, but yeah, you can see that it is able to run the software here. Yeah. Let me now show you one another interesting thing that I was able to run on top of this. Yeah. So it has completed now, and it shows that it has successfully passed all of these classifications. So now what this is. So here what I am doing is I already had the RISC-V sock here. As you can see, I already had this simulation or the virtual prototype of this RISC-V sock. And on top of it, I have written my own ignition accelerator. So this is the source. It is very basic, but I have given it like some registers, and you can see the registers here. And this is the source of our own accelerator IP. So let's say at Ignition, if I want to create my own accelerator IP, but I didn't have the time for writing the RTL, or I was not clear on what kind of registers I should create, how it should connect to the rest of the system, and so many uncertainties, right? So I can simply create the accelerator code here in Python, and then I can integrate it with the rest of the sock here. And as you can see, I also have the MNIST classification source here. So this is the C source and this is the header. Then I compiled this, and in this header you can actually see the weights. So these are the weights that goes into the model classifier, and this is all compiled using a RISC-V 32-bit compiler, and then it creates a I think you should see somewhere it creates the binary for it. Yeah, I think in the bin. Yeah, somewhere here there is the binary for this as well, which I have booted into my system, into the rest of the RISC-V system. And what you just saw here, what you just saw in this terminal, the classification work here is being done by the accelerator. So not the RISC-V core. So the RISC-V core is itself simulated, but it is offloading the classification tasks to the MNIST handwritten classifier accelerator, which I just showed you is written in Python in this case. And I am seeing that my idea is validated. So the register interfaces that I chose and the kind of computation it does is sufficient for this classification. So once I am happy with this, I can now proceed with the RTL. Yeah, so this is the kind of model that you should also follow, where you have your idea and you write a model for the idea and then validate the model against already running model. And once I am happy enough, I can proceed with the RTL, because I already know that my thing is working here. So there is no issue in writing RTL now. Yeah. So any questions on this? If not, I'll proceed because we're almost over the time. So this here is the demo that I just showed you, and there are other demos as well. And below here you can see that there is a COSIM, very related COSIM, which is part of our let's say next stage in this one, where we have now validated our idea using a Python peripheral model, and now it is the time to write it in RTL. So again, when we write this our own accelerator using RTL, we are not going to again jump directly into synthesis. We will again come back in the VP loop and then again co-simulate it with the existing VP. So this time it is not a Python peripheral, but actually the RTL code. So this is something that's next in line. And when this is again done, we are fully validated that yes, our system works, and I didn't even require a hardware or a board or a RISC-V core, or I didn't even go to the market or get some hardware for that. I did the whole thing, whole experimentation entirely on my laptop using software, and I'm now happy that my chip can be actually fabricated, or at least I am happy that the design works. Yeah. And here is the crucible or our tools, let's say narrative here, that in order to run any of these demos, you don't require to do the whole setup. You don't need to run the tools or set up the whole environment. You can just run one command, igni workspace sync, and you are able to replicate this entire experimentation on your local setup as well. So these slides go into the details of what I already showed you. So I'll not go over this. I'll briefly go on this stage. So I created the PyTorch model learning, then I exported it in C header, then I cross-compiled it using a RISC-V32 core, then I loaded it into the VP, and then finally I ran it on the RISC-V core. And I also showed you the terminal. It was different from my own local setup. Yeah. So as I already said, all dot product operations on the experiment that you just saw are dispatched to the accelerator via MMI register write. So using the registers, the core communicates with the accelerator, and the VP executed them correctly in every case. The firmware was unmodified from what would run on the actual silicon. So when my accelerator silicon comes, I can just port the exact same firmware and it will run without any issues. Yeah. And this is what I just said about the environment replicability. You don't need to do anything. So this is the problem without Crucible, and these are the points that you can again refer if you have to, let's say, compare it to Lieberlane or any of the existing flows. Yeah, so you still, of course, those flows help us, but you still have some of the corners where it is not completing or not completely giving you the freedom to, let's say, just get started with the experiment. If I am a VLSI engineer, my focus should be on solving and dealing with VLSI tasks and not the environment or the reproducibility or the setting up stage of the project. Yeah, so this is the whole idea. So yeah, again highlighting the same point, the one developer, one engineer, but many heterogeneous flows. You can have many versions of all these tools. You can use one version of Renode on one workspace and another version of Renode on another. You can use any compilers, and as you can see, one of our demos, upcoming demos, actually is going to use the tools that one of the participants just highlighted. So we are not separate from them, we are building on top of them. Yeah, so you can see open road and open lane is part of that demo itself. Yeah. Yeah, I think this is the next steps. So yeah, I already went through this, and this is what I would like to highlight that we are currently working. We want to see if we can go through a full SOC and do every stage. So as I introduced the pre-RTL stage, we want to be able to go through all the stages and the last stage, which is the GDS, which means you are tape out ready. So finally, I will conclude my presentation on virtual prototyping also. So the idea is very simple. The chip can exist without silicon as well. You can emulate or simulate it using software, and all the benefits of the software world carry forward to the hardware aspect as well. Yeah. So that's all from my side. If anyone has any questions, please let me know.